Physics Part 395. Nuclear Fission Reactor. There are several possible fission reactions which may occur in a nuclear reactor. Most are represented by general equation. The nuclides formed in this reaction are called the fission fragments. The figure illustrates a pressurized water-cooled, rather PWR, inside the reactor. The uranium-235 is placed in a long fuel rod which are surrounded by heavy water, water in which deuterium atoms, hydrogen 2 take the place of normal hydrogen 1 atoms or graphite. The role of these materials is to slow down the neutrons released during fissions. This is important because slow-moving neutrons are more readily absorbed by uranium-235. Materials such as heavy water or graphite which slow down the neutrons are called moderators. The number of neutrons available to trigger a further fission reaction is controlled using control rods of boron and cadmium. The substance readily absorbs neutrons by pushing the rods further into the reactor core. The number of the neutrons absorbed increases and the rate of the fission reactions decreases. If the rods are pulled out a little, fewer neutrons are absorbed and the rate of fissioning increases. Ideally, the rods should be adjusted so that the fission reactions proceeds at a constant rate, that is, it neither accelerates nor deaccelerates. The energy released during fission reactions is seen mainly as the kinetic energy of the resulting lighter nuclei and neutrons. The fission fragments, when the fission fragments are slowed down, the heat energy produced is removed from the reactor by circulating coolant. This heat energy is then used to produce high temperature steam in a heat exchanger. The steam is used to drive turbine generators. There are two main types of nuclear reactors used for the commercial generation of electricity. These are pressurized water-cooled reactors, PWR, and the advanced gas-cooled reactors, AGR. In the PWR, water circulates through the reactor vessels at a high pressure, typically at 150 atmospheres. At such pressure, the water does not boil, even though its temperature may be as high as 300 degrees Celsius. This superheated water passes into the heat exchanger through a series of pipes surrounded by water at much lower pressure. The low pressure water absorbs heat energy and changes into steam, which then drives the turbines and electricity generators. In AGR reactors, helium gas at a temperature of about 600 degrees Celsius is the coolant again. Again, energy is transferred from the core to water to a heat exchanger in order to produce the steam to drive the turbines. Next, we have got the section, very important section, right next to nuclear fission. We have got 13.11, and that's what we call nuclear fusion, a very significant part of this chapter. Nuclear fusion. Most of the energy on Earth comes from the sun when it is produced by nuclear fusion reactions. Light nuclei, such as isotopes of hydrogens, join together to produce heavier, more stable nuclei, and in doing so release energy. one of these fusion reactions.